We are diving straight into the MMGR benchmark paper today. That's Multi-Modal Generative Reasoning.
And this is really essential reading for anyone tracking world simulation models.
So for today's summary, what's the immediate takeaway?
The big one, the thing everyone needs to hear, is that even the best models, Sora 2, VO3, all of them show this massive gap.
The gap between what exactly?
Between how good they look and how well they can actually reason. High perceptual quality is absolutely not translating to robust reasoning.
The videos look amazing, they're perfectly rendered, but the world inside them is, well, it's broken.
It's fundamentally broken, yeah, physically and logically. And the MMGR framework is built to prove that. It tests 5 core abilities.
Physical, logical, spatial, temporal.
Exactly. And it uses tasks like maze solving, complex physics, sports, things that require real understanding.
And the result is that they pretty much all fail.
They do. They fail at symbolic processing. They fail at keeping the physics consistent. It's just pattern matching.
Not real understanding.
Right. And the paper points to the bottlenecks, not enough symbolic reasoning data, and, the models are optimized to just look good.
So they're rewarded for visual fidelity, not for making logical sense.
That's the whole story in a nutshell.
Okay, so let's unpack that foundation. The benchmark is built around 5 reasoning abilities, and the researchers link this to concepts of core knowledge in human cognition.
They do, and that's a key point. The goal here is to push these models beyond just, fancy animation.
By actual world modeling.
Exactly. Do they get the rules of the universe, or are they just good at copying what those rules produce visually?
Okay, let's go through those core pillars, starting with physical reasoning.
So physical reasoning is basically intuitive physics. Object permanence, gravity, collisions, how different materials behave. It's the absolute baseline for any real simulation.
The paper uses a great example to test this. A ballet dancer doing a fouette turn. But I have to ask, isn't that a super common thing in training data? How do you know you're testing physics and not just, imitation?
That's a great question, and it's why they chose it. A fouette isn't just one thing. To get it right, the model has to understand the flex of the shoe. That's material deformation. It has to understand conservation of angular momentum, how the spin speeds up and slows down as she moves her limbs.
Right.
And centripetal force to keep her balanced. A model that just imitates a video will get that stuff wrong. You'll see wobbles, weird spin rates, impossible balance. It has to be coherent over the whole video.
Got it. That really clarifies how tough the test is. Okay, next up is logical reasoning, which you said is the big weak spot.
It really is. This is the symbolic processing part, what some people call system 2 thinking.
So following rules, abstract concepts, if A, then B kind of logic.
Exactly. And if a model is only built on correlation, it just can't do that. It can't generalize or hold a consistent logical state. It's why they fail these tasks so badly.
And then we get to the spatial side of things, which they split into 2.
Yeah, 3D and 2D. 3D spatial reasoning is about building an internal cognitive map of the world.
Like a persistent GPS of the scene.
You got it. It has to know where things are even when the camera isn't looking. It's crucial for navigation and just keeping the geometry consistent.
And how is that different from 2D spatial reasoning?
2D is all about the image plane. Think of it like reading a flat map. It's about understanding the layout and position of things from one single viewpoint, but it doesn't need that deep internalized 3D model.
And I guess temporal reasoning, the 5th ability, is just woven into all of these dynamic tests.
It's everywhere, yeah.
Okay, so this is where it gets really interesting. How do they actually blend all of this into benchmark tasks that really test for competence?
The MMGR uses these really clever complementary domains. We can talk about physical common sense later, but let's start with the abstract reasoning domain.
Which is more about the logical and 2D spatial skills.
Right. And the first one is maze solving.
A classic test of sequential planning.
Exactly. It's a really clean test for 2D spatial awareness, logical path finding, and then executing that path over time. But the failure criteria are what's really fascinating. They're incredibly strict.
We're not just talking about, did the agent find the goal?
No, not at all. We're looking for fundamental violations of the rules of that little world.
So what are the criteria?
2 big ones. Cross wall, which is just what it sounds like. The agent touches or goes through a wall.
Pretty basic rule to follow.
You'd think so. And the other is maze changed. This is where the maze itself just morphs in the middle of the video. It shows the model has 0 scene consistency.
And they have a great example of this with VO3.
They do. The agent actually gets to the target, but the video is still a failure. Why? because halfway through, a wall just vanishes.
Wait, it deleted a wall to solve the maze?
It seems so. It gets to the goal, but only by cheating, by breaking the environment. The model is clearly optimizing for the endpoint, not the valid journey.
That's not problem solving. That's just a model can't maintain the world's integrity. That's a huge red flag.
It is, and they ramp up the difficulty too, using things like depth-first search to generate these mazes, from tiny 3x3 grids up to really complex 13x13 ones.
So it can't just memorize layout.
It has to actually generalize a pathfinding strategy, which makes the failures even more telling. If it can't understand a simple rule like walls are solid in a 2D maze, what chance does it have in a complex 3D world?
None. Okay, what about the other abstract task, Sudoku solving?
This one is almost purely logical and 2D spatial, and the metrics are similar. Did the clues change? Did it violate the rules? And did it actually complete the puzzle?
And what's the big failure mode here?
This is where the paper introduces a really cool concept they call the correction paradox, or sometimes toxic reflection.
Toxic reflection, I like that.
Yeah. So in a simple 4x4 Sudoku, VO3 did something that looks like self-reflection. It went back and changed a number it had already placed.
Which sounds good, right?
Yeah,
Like it's
yeah.
correcting a mistake.
It sounds good, but the correction almost always broke another rule. It would put a repeated digit in the same row, or even, bizarrely, change one of the original clues.
So it's like it saw a visual pattern that felt wrong, but its attempt to fix it was just noise. It made things worse.
Precisely. Its reflection is just visual and random. It's not doing a system-level check for logical errors. It's just swapping one mistake for another, often worse, one.
Okay, so models are clearly struggling with these abstract symbolic rule systems. What happens when you embed those kinds of rules inside a realistic generated 3D world? Do the same problems follow?
They absolutely do. And that brings us to the simultaneous localization and generation task, or SLAG.
SLAG. It's an extension of SLAM, but with a generative mapping requirement.
Right. The setup is a humanoid robot navigating a complex indoor scene, kind of like a dollhouse view, and it has to generate a 2D top-down map of its path as it goes.
And there are hard physical rules.
Yeah.
Right? It has to actually climb stairs. It can't just float up.
Exactly. This tests 3D spatial and physical reasoning under huge pressure. And the closed-source models had some very specific failures.
Let's start with VO3.
VO3 success rate just plummets as the scene gets more complex. It goes from over 73% on a simple floor plan down to under 47% on a multi-floor scene.
And making the video look prettier didn't help.
Not at all. Better graphics do not equal better thinking.
And what about Sora 2? The paper said it was just chaos.
Total scene hallucination. It would just spontaneously generate a second identical robot in the middle of the scene.
Wow.
And the main agent would just walk straight through solid objects. It got a 0 on the object semantic score. The objects had no meaning, no permanence.
And then there's 1.2.2, the open model, which had a different but equally bad problem.
Yeah, 1.2.2 had great agent motion. It looked smooth, but the environment itself was completely unstable.
What do you mean?
As the camera moved, things would just vanish. A glass door would disappear. New pillars would pop into existence. It's a total failure of background object permanence. You can't simulate a world that's constantly rewriting itself.
This all leads to what might be the most important finding for anyone building these things, the plausibility gap.
Yes. The automated metrics are basically lying. They are massively inflated compared to what a human sees.
What's an example?
On a simple floor, the auto-eval gave a physics validness score of almost 46%.
Okay.
Human evaluators looked at the same videos and gave it 5.56%.
That is a staggering difference. Why?
Yeah.
Why are the machines grading themselves so highly?
Because the auto-evaluators are good at one thing, checking for task completion. Did the robot end up on the red square? And on that, humans and machines agree.
But they miss all the impossible stuff that happened along the way.
They miss everything. The clipping through walls, the floating, the teleporting. Humans see that impossible movement immediately and say, this is wrong, and the whole score collapses. The machines don't see it.
So the models are gaming the metrics. They're optimizing for the final camera shot, the destination, not the physically valid journey to get there.
That's it, exactly. And it shows we just don't have the automated tools yet to catch these deep physical common sense violations.
Let's pivot to the physical common sense domains. This is where they really turn up the heat, right? From solid-on-solid friction to fluid dynamics.
This is where it gets incredibly rigorous. They use 4 fine-grained metrics, and this is the important part. A video has to score a 1, a perfect score, on all 4 simultaneously to be counted as a success.
Anything less is a total failure.
A total failure of the simulation.
So what are the 4 constraints?
First is physics accuracy. Does it obey gravity, momentum, friction? Does it stick to the scenario's focus? If something floats when it shouldn't, it fails.
Makes sense.
Second, motion quality. Is the movement smooth and continuous? No jerky frames, no weird jumps in time.
Third has to be visuals.
Visual realism, yeah. Fidelity, consistent lighting, no weird artifacts. And finally, prompt adherence. Does the video actually match the text prompt?
That overall success definition is so critical. A single physical flaw invalidates the whole simulation.
It has to. But we did see one really interesting success story.
Which was?
VO3 actually nailed the parasail inflation scenario.
That seems really complex. It's not a rigid body, it's a soft dynamic system. Why would it succeed there?
That's the question. It accurately captured all the complex physics. The canopy deforming as it fills with air, the pressure building, the lines tightening as they take the load. It got perfect scores on all 4 metrics.
So what's the takeaway from that?
It suggests that modeling these soft fluid-life dynamics, which is more about synthesizing a plausible flow, might actually be easier for these models than rigid body dynamics, which requires precise calculated interactions like contact and friction.
Which fits with the idea that solid mechanics are the biggest hurdle.
Oh, absolutely. Solid interactions, pushing, colliding, friction. That's consistently the hardest category for every model. And you see it in the AutoEvil scores again. Their success rate on hard physical cases dropped from over 53% on easy to just 22% on hard.
It just reinforces that these models don't have a real internal physics engine.
Not a generalized one, no.
So let's step back. What does all this mean for the future of world simulation? We have these visually stunning models that are violating fundamental physical and logical rules.
It's a clear signal. The models are learning to be incredible pattern matchers, incredible visual correlators. They are not learning symbolic reasoning or causal consistency.
And the performance hierarchy we see, with the big closed source models on top.
It suggests progress is mostly coming from scale, just more data to pattern match, not from real architectural breakthroughs that would teach model physics from the ground up.
So scale is just papering over the cracks, but it's not fixing the foundation.
That's the perfect way to put it.
Let's revisit those 3 key bottlenecks the paper highlights, because fixing these seems to be the roadmap for the next generation of AI research.
Okay. First, we have a massive data scarcity problem for structured symbolic reasoning.
Right.
Second, the architectures themselves are biased. They prioritize making the current frame look good, local plausibility, over making the entire video make sense, global consistency.
And third is the objective function.
The optimization, yeah. We are rewarding perceptual fidelity, not logical validity. We are, in effect, training models to be amazing artists, but really poor engineers.
Which leads us to the final provocative thought we want to leave you with. What is it actually going to take to get from just sophisticated animation to a genuine, causally consistent world simulation?
I think future research has to make a fundamental shift in focus. We need architectures that can actually decouple the reasoning state, the plan, the logic, the physics, from the final visual rendering process.
So 2 separate tracks working together.
Exactly. And that means building in new objective functions, new rewards, specifically for causal consistency and following the rules, not just for looking pretty. The real challenge is moving beyond just simulating what gravity looks like, actually teaching a model why gravity works.
Because until we do that,
these simulations will always be beautiful, but they'll also always be brittle.